Reviewing pulmonary ventilation. And let's just remind ourselves what the driving force here is. So the driving force for ventilation is basically our pressure gradient, right? Our change in pressure, which is our atmospheric pressure minus our alveolar pressure, right? That's what's going to create that gradient. The other thing we want to remember is that this is a cyclical process. So the gradient exists to drive air in, and there's a period of rest. So that period of rest is owed to the dissipating of the gradient. So there is no gradient in between the cycles. So at rest, the pulmonary atmospheric pressure is equal to the pulmonary alveolar pressure. Therefore, there is no gradient. So there is no flow. So that's what's happening in between both of those cycles. We also want to describe the atmospheric pressures, just to remind ourselves here. The pulmonary atmospheric pressure, we describe that number as being absolute at 760 millimeters of mercury, meaning that that's the actual reading. So this is the absolute or actual reading. And then in terms of the relative reading, the value that we're going to consider, just to make things simple, is we're going to zero that out since that's pretty much unchanged at 0 millimeters of mercury, and that is our relative atmospheric pressure. So all the other pressures that we'll consider, we'll use them, or we'll use 0 as sort of the reference point for how those other pressures are changing. So let's look at two scenarios here. Oh, wait, one other thing we need to describe, the transpulmonary pressure. Let's describe that here. So we describe the transpulmonary pressure. We also talked about this as being our distending pressure. Oops. Also known as our distending pressure. Is our alveolar pressure minus our intrapleural pressure, right? This pressure in between the pleural space. And this is usually equal to -4 millimeters of mercury at best, which means there's a negative intrapulmonary pressure um, in between that, the spaces of that pleural cavity. So let's describe two scenarios here just to illustrate this during inspiration and during expiration. So let's start with inspiration. And expiration. And we're basically looking at the chest cavity. So I'm going to draw my version of the thoracic cavity here. And then we're going to put two lungs inside. Right, so this is our lung. And this is our intrapleural space. We also want to draw the diaphragm. Now we know that during inspiration, the diaphragm is nice and flat. Right, it's flattened out. So let's think about what's happening in terms of the pressure in our alveolar versus the pressure in the intrapleural space. So during inspiration, we need to remember that the atmospheric pressure is 0, The alveolar pressure is going to be more negative. In order to drive air in, the alveolar pressure must be lower than the atmospheric pressure in order for the direction of airflow to be inward. So our alveolar pressure here, and we can look at again both the absolute and the relative values. The absolute value here is about 758 millimeters of mercury, or the relative, so 0 to subtract 2, would be negative 2 millimeters of mercury, right, compared to our atmospheric pressure. So with this gradient, 760 in the atmosphere, 758 in the alveolus, now we have a driving force that moves air in this direction. So airflow goes down to the alveolus. So let's describe that here. Okay. We also want to think about the intrapleural pressure. Sorry, before we get to that, let's talk about the intrapleural pressure. So the intrapleural pressure in between the pleural space is going to be absolute of 754 millimeters of mercury, right? Remember, we said it needs to be negative 6, negative 4 from the alveolus, but then negative 6 from the atmosphere. So these two values, excuse me, alveolar pressure minus intrapleural pressure should equal negative 4 millimeters of mercury. Sorry, stumbling on my words here. So this should be 4 millimeters of mercury difference. Okay, so if this is 758, this is 754, which is negative 4. Sorry. With respect to the atmosphere, this ends up being negative 6 millimeters of mercury. Okay, so our alveolar pressure, negative 2, which creates our airflow, our intrapleural pressure, which still keeps the lungs expanded. Remember, this pressure needs to stay negative 4 from the alveolar pressure, negative 6 from the atmospheric pressure, in order to keep the lungs distended, right? That's our distending pressure, our transpulmonary pressure. So this is what that number would look like as the alveolar expand and air comes in order to maintain that negative pressure in between this space. So let's describe the differences here. So this is inspiration, which means that our atmospheric pressure must be greater than our alveolar pressure, which also means our alveolar pressure must be negative, right? Which we can see that here it is. And this is what's happening during inspiration. Let's look at the alternative scenario during expiration. So again, our thoracic cavity, oops, not the best thoracic cavity. Okay, so our thoracic cavity, our lungs, and then now we can actually draw our diaphragm relaxed. During expiration, we know the diaphragm is curved in its dome shape, curved upward, right, which means it's relaxed. Let's think about our pressures now. So here we're going to have alveolar pressure that must be positive. In order for airflow to move in the opposite direction, our pulmonary, our alveolar pressure, intraalveolar pressure, should be equal to 762 millimeters of mercury, right? So 2 above the atmospheric, which is, in terms of the relative pressure, that would be positive 2 millimeters of mercury. Okay? And then similarly, our intrapleural pressure here, this is going to change as well, but it's still going to maintain that 4 millimeters of mercury difference between the alveolar pressure. So if the alveolar pressure is +2, this is going to have to be -2, right? 4 millimeters of mercury more negative than the alveolar pressure. So our intrapleural pressure is now going to be equal to 758 millimeters of mercury, and the relative value is -2 millimeters of mercury. Okay, maintaining that, sorry, maintaining that 4 millimeters of mercury difference, negative pressure in that space. So again, let's summarize here. The alveolar pressure in this case must be greater than the atmospheric pressure. Which means that the alveolar pressure must be positive, right? Which we can see that it is here. All right. And then just to remind ourselves that this is the diaphragm contracted, and this is the diaphragm relaxed. Right? So just reviewing what we described on Monday, just kind of illustrating it all together, how all of these pressures are important in different regards. In this instance, we're moving airflow in the opposite directions. We're moving airflow here in the opposite direction for expiration. Another thing I want to point out that is not illustrated here, but is also important is Boyle's law. We talked about how Boyle's law changes the shape of the cavity, the shape of the cavity changes the volume of the cavity first. So in this instance, when the diaphragm flattens out, volume goes up here. So increase volume means decrease pressure, right? And then that is what drives airflow out. So this is how this becomes more negative. As volume goes up, the pressure here goes down. Opposite is true on this side. So again, when we make the cavity smaller, that makes the volume go down. Over here. So here, volume goes down, which makes pressure go up, which is why it's positive here. So that Boyle's law, together with the descending pressure, together with our pressure gradient, all of those factors come together to allow for the cyclical process of ventilation. Okay. And then in between these phases, we have rest. So alveolar pressure becomes 0 at some point, right? It's going to go from 0 at rest, then it swings positive for expiration, then it comes back to 0, then it swings negative for inspiration. And again, we keep that sort of cyclical rhythmic process for ventilation.